Measuring a physical system always yields a real number because the underlying mathematical operator coincides exactly with its own adjoint. Functional analysis defines these observables as linear operators acting on a Hilbert space, a complete vector space equipped with an inner product. For any bounded operator T, the adjoint T star is the unique operator satisfying the inner product equality for all vector pairs. An operator is self-adjoint, or Hermitian, if it equals its adjoint, meaning the action on either side of the inner product is identical. This symmetry ensures that every eigenvalue of a Hermitian operator is a real number, preventing non-physical complex results in measurement. Eigenvectors corresponding to distinct eigenvalues of a Hermitian operator are necessarily orthogonal, representing mutually exclusive physical states. In infinite dimensions, most physical operators like position or momentum are unbounded and cannot be defined on the entire Hilbert space. Unbounded Hermitian operators require a dense domain, a subspace where the operator is well defined and which sits everywhere near every vector. A symmetric operator satisfies the inner product identity but might have a domain strictly smaller than its adjoint's domain. The Hellinger-Toeplitz theorem states that any symmetric operator defined on the entire Hilbert space must be bounded. True self-adjointness requires the operator and its adjoint to have identical domains, a prerequisite for the spectral theorem. The spectral theorem generalizes the concept of diagonalization to infinite dimensions, decomposing operators into a continuum of projections. Instead of a sum of discrete eigenvalues, we use a projection-valued measure to integrate over the spectrum of the operator. A discrete spectrum occurs when eigenvalues are isolated, typical for particles trapped in a potential well, like an atom. Free particles exhibit a continuous spectrum, where any value within an interval can be a result of a measurement. The position operator multiplies a function by the independent variable, acting as a fundamental self-adjoint observable in functional analysis. The momentum operator involves a derivative and the imaginary unit, ensuring its symmetry through integration by parts. Hermitian operators that do not commute cannot be measured simultaneously with infinite precision, leading to the uncertainty principle. The product of the variances of two non-commuting self-adjoint operators is bounded below by their commutator value. For a self-adjoint operator, the resolvent set consists of all complex numbers where the shifted operator has a bounded inverse. The spectrum is the complement of the resolvent set, and for Hermitian operators, it is always a subset of the real line. Continuous functional calculus allows us to apply continuous functions to self-adjoint operators, creating new operators on the same Hilbert space. Self-adjoint operators generate strongly continuous one-parameter unitary groups, which describe the time evolution of quantum systems. Stone's theorem provides a one-to-one correspondence between self-adjoint operators and these unitary groups of time evolution. The Hamiltonian operator represents total energy and is the most significant self-adjoint observable in any physical model. Compact Hermitian operators behave much like finite matrices, always possessing a complete set of orthonormal eigenvectors with eigenvalues approaching zero. Rees-Schauder theory confirms that the non-zero spectrum of a compact operator consists only of isolated eigenvalues with finite multiplicity. For compact Hermitian perturbations, the Fredholm alternative determines whether operator equations have unique solutions or non-trivial kernels. The norm of a bounded Hermitian operator is exactly equal to the supremum of the absolute values in its spectrum. A self-adjoint operator is called positive if its inner product with any vector is always a non-negative real number. Every positive self-adjoint operator has a unique positive self-adjoint square root, a vital tool in polar decomposition. Any bounded operator can be decomposed into a product of a partial isometry and a positive self-adjoint operator. In quantum statistical mechanics, density matrices are trace-class positive operators whose trace is normalized to 1. The essential spectrum consists of points that are not isolated eigenvalues of finite multiplicity, often representing scattering states.
Weil's criterion characterizes the spectrum through approximate eigenvectors, sequences of unit vectors that almost satisfy the eigenvalue equation.
Symmetric operators that are not self-adjoint are studied using deficiency indices, which measure the gap between the operator and its adjoint. An operator has self-adjoint extensions if and only if its deficiency indices are equal, allowing for different physical boundary conditions. The Friedrichs extension provides a canonical self-adjoint operator for any densely defined symmetric operator that is bounded below. The Cato-Relic theorem ensures that adding a small symmetric operator to a self-adjoint one preserves self-adjointness. The Cayley transform maps self-adjoint operators to unitary operators, providing a bridge between linear and circular geometries in Hilbert space. We calculate the value of an observable in a state by integrating the identity function against the projection-valued measure. The expectation value of an observable is the inner product of the state vector with the operator applied to that state. The variance of a self-adjoint operator measures the statistical spread of measurement results around the mean expectation value. The identification of observables with self-adjoint operators is the core of quantum logic, ensuring consistency between math and reality. Mastery of Hermitian operators unlocks the ability to predict the behavior of complex systems, from subatomic particles to quantum computers.